What's up, YouTube? Matt Vogt. Wanted to talk to you today about the cool advancements in artificial intelligence and then how we can use those in the military, specifically for training and simulation, planning, and then wargaming. A lot of really cool things in developments in AI for games. How do we take those in the corporate world and in the military and apply those? That's what we're going to be talking about today. The future is bright. We use games as hard problem sets to discover novel AI solutions because these games are analogous to the real world in a lot of ways, although there are rules. Games allow for easy reinforcement of behavior and decision development in scenarios that require perception, decision-making, and action. If you want to think about it, these three areas are the same exact areas we need significant advancement in robust autonomy development and employment. We need future AI to be able to compete and coordinate with humans and other agents in these complex environments. AI's ability to exhibit superhuman performance in games is nothing new. AI has been defeating humans in games since before the term AI even existed, actually. With the chess-playing robot, El Ajedrecista, the chess player, able to checkmate humans in a three-piece game. This was in 1919. That's crazy if you want to think about it. Recently, the explosion of resistor count, if you want to think about Moore's Law, and novel applications of design of AI, advancements have been made and bridge the gap between what we used to call brute force solutions to more elegant reinforcement learning designs. So what does this mean? This means significant advancements beyond what we ever thought possible. It takes this significant difference in intelligence to solve advanced games like StarCraft 2 in this example, which has long time horizons, partially observable states, ambiguity, hundreds of actors, and 10 to the 26 possible actions each step. That is astronomical. If you want to think about it, of possible actions, that's more actions than there are stars in the night sky or grains of sand on Earth. Mind-blowing. Anyways, StarCraft 2, for those who aren't gamers, is a real-time strategy game that balances micro-tactical level with operational and economic decision-making necessary to challenge competitors with a balance of focus and effort. So 20 years this game has been out, it is still one of the largest esports tournaments games, pitting pro gamers against one another for millions of dollars in prize money each year. In 2019, AlphaStar was developed by DeepMind, who now and just recently got bought out by Google, defeated two professional gamers from Liquid Mana and TLO, solidifying AI's dominance over the more complex games to date. DeepMind uses a combination of new and existing general-purpose techniques for neural network architecture, imitation learning, reinforcement learning, multi-agent learning to train AlphaStar to superhuman levels. Basically, AlphaStar used AI in multiple ways to sense itself, its environment, and the enemy. That's exactly everything we're trying to do in the military, right? And then it makes recommended decisions and actions to maximize the likelihood of victory. Although parameters and strategies are initially sampled and mimicked from human play, build orders, and unit makeup, its actions then depart from these human norms. It learns to play with itself and better itself on unprecedented timescales. To develop multiple different strategies of gameplay, AlphaStar needs a little bit of help initially. If you want to think about, for instance, a build geared heavily on micro-tactics of ground units, it would be very difficult, for instance, to introduce a little bit of air into that. It would reduce performance. These small tweaks would be essentially punished and reduce performance. And that strategy would devolve back to that very narrow application of micro-tactic heavy ground strategy. This could be expressed similar to a mountain climber with very near vision trying to seek the highest mountain, but not being able to see very much in any direction. And once he gets to a little small mountain, everywhere around him is down, and he's not able to see the large mountain in front of him. In order to develop disparate strategies, agents in AlphaStar for StarCraft 2 here were trained using supervised learning initially to mirror discrete human strategies. This ensures a wide variety of relevant modes of play that can be explored before they're killed off. Once these agents are trained with novel strategies mirroring humans, they're ready to go, work optimizing perception, decision, and action. That's the three that we've talked about earlier. Perception, decision, action through reinforcement learning. These basically were just really, really beefy computers that chewed through hundreds of years of self-play to optimize these models. The interesting thing with StarCraft 2 that differs from other games like chess and Go is there's no best strategy. There's deliberately designed strategies that balance the other strategies. If you want to think about it like a game of rock, paper, scissors, in the case of StarCraft 2, Stalkers defeats Void Rays, Void Rays defeats Immortals, Immortals defeat Stalkers, and this continues for every other race. AlphaStar must learn the best response against a mix of these rock, paper, scissors strategies without chasing the cycles. The agents are trained against a mix of strategies itself and previous versions. These different strategies thrown into league play basically play each other on 32 tensor processor units, TPUs, for 44 days. That's a lot of play. And this involved 900 different agents, so this was really a lot of training. What some called impossible before, AlphaStar defeated Liquid's TLO 5-0 and Mana 5-0 as well. Crazy. What's even more impressive is that DeepMind had to hamstring AlphaStar so it didn't have any advantages over the human competitors. Instead of just letting it go at the game, they had to hamstring it so that it was, quote, more fair. Instead of being able to view everywhere on the map simultaneously, AlphaStar was required to move the camera similar to humans, and latency was actually introduced artificially to slow the computer down. AlphaStar's actions per minute were actually significantly reduced as well, to about half that of TLO and Mana's. Any kind of artificial intelligence in the military wouldn't have these impositions in place. We would just open it up to see what it's capable of. Here are a couple of AlphaStar's opponents discussing its behavior, and this is fascinating.
I was very, very disappointed I lost this game because I thought I have everything that I need to defend this. I wasn't expecting the AI to be that good. Everything that he did was proper, it was calculated and it was done well. I thought I'm learning something. Yes! Yes! It's much better than I expected it to be. I would consider myself a good player, right? But I lost every single one of 5 games.
This is an incredible development, and although StarCraft 2 is just a game, there's significant learning from each of these efforts. There are lessons learned inside of StarCraft 2, such as build order, composition of armies, control of units, but there's also larger lessons, and this is more important, more general than StarCraft 2 play. For instance, neural network architecture needed to win StarCraft 2 is useful in modeling long-term sequences of likely actions based on imperfect information. From optimizing performance in a dogfight to simulation and wargaming and operation, we need greater ability to predict not just the results of our actions, but the whole sequence of action through the rest of the operation, many times per second. The challenges with making complex predictions over long sequences continues to be a challenge for specific applications like weather prediction, language, and human behavior. Have you heard of chaos theory? If either the model or the initial parameters are inaccurate, their prediction into the future will become exponentially more inaccurate. These inaccuracies in complex, tightly coupled systems is what many would call a wicked problem. If you want to look at this double rod pendulum that's swinging, it looks like the behavior initially is quite predictable, and then it departs drastically and very wildly swings. The ability for us to accurately represent air, ground, and sea units in wargames, their physical interactions with each other, the environment, and then predict their behavior are paramount. Without accurate measurements and modeling, our wargames and training simulations will never be able to see some of the gains that we just talked about in games like StarCraft 2 and the AI that has competed in those. The prospects here are great. Two examples for this application of artificial intelligence are obviously training simulation and wargaming. Imagine this scenario. You're a young F-22 pilot. You've just mastered basic aircraft flight, navigation, and formation. Next on your rigorous training pipeline is basic fighter fundamentals, BFM, and dogfighting. What would be most beneficial for this training pipeline here? To read about the capabilities, armament, and turning characteristics of the J-20, fight against that in another F-22 that's acting like a J-20, or fly in a realistic simulator mirroring the exact characteristics with a significantly developed artificial intelligence and tactics of that J-20. That would be really great for that young F-22 pilot to spend a couple days honing his skills in that simulator on the cheap with that AI and that J-20. Let's take another couple steps from that, if you will. It might be good to send that F-22 and J-20 into, let's say, hundreds of thousands of dogfights with different entry parameters, different loadouts flown by that AI to determine the optimal tactics, loadouts, and potentially any modifications necessary to that F-22. Sounds like a smart idea to me. What about a 2v2, 4v4, 2v4, 10 versus 16, or other engagements? There is no way of being able to tell or tabletop those engagements accurately, or determine in any reliable way the possible matchups that could exist. You need that AI's agility assist here. AI can provide the speed, strength, coordination, and flexibility to run these virtual fights, both beforehand and then even if that time comes in the real world. So, what do we actually want here? What's our goal? What's our end state? What should we be searching for? This is simple. We need the ability to predict outcomes before we even engage in that fight. One of the most popular Sun Tzu or Sunza sayings here applies. If you know thy enemy and you know thyself, you will not be imperiled in 100 battles. This seems simple, but this is exactly what we're trying to get at. We need the ability to efficiently, effectively wargame engagements at the tactical through operational level. This means simulating engagements on a more robust level than just numbers on a spreadsheet. Each individual engagement needs to be accurately modeled, as detailed as possible, and controlled by AI, and then these engagements need to be built like building blocks and then connected to a whole of operation. Accurate interactions between these blocks are imperative. The tightly coupled wargame complex systems mirror a lot of what we just talked about in StarCraft II's work by DeepMind, and it concluded that solving game theory problems with imperfect information over the long term, in real time, over a large action space is possible. We're just now getting there. The corporate world and academia are doing the heavy lifting here. We just need to learn from their lessons and implement their best practices as we open our eyes, discover the realm of what is possible. These are exciting times. Wow, you stuck it out through the end. That means you like this content. So I definitely appreciate, hit the thumbs up, like this, leave a comment, and definitely subscribe so you can see future content like this. Appreciate it. See you.